just knock over all the
We're all looking from Pittsburgh? Yeah, where are you all from?
I'm from Nazareth. We're on the east side of the state, Lehigh Valley.
Okay, it's a long way.
Yep.
So if you were
I'm out so
where is it? If you can go for the speakers, that'd be great. Yeah, I just grabbed this.
No, you're right. You're correct.
Okay. We should separate this.
Okay.
First. You go. Welcome, everybody.
Thank you so much. We're so glad to spend time with you this morning, and really our goal is to work with you to help support your vision and your needs, and we're hoping that today we can give you information that will start that process. I'm Eileen Owens. I'm Director of Technology and Innovation for South Fayette School District.
And I'm Shad Wachter. I teach 3 through 5 technology literacy, and I also assist with the STEAM program at our school.
So what we want to do is kind of give you a quick overview of who we are. Today we're going to go over roughly the fact that we have a K-12 pathway in computational thinking and computer science / STEAM. And within that, we have through lines that we've developed. So today we'll talk about a rough overview of the pathway, what the through lines are, and then we're going to go into how math, especially spatial reasoning and discrete math, work within computer science at this very young grade level. Okay? So the first thing is we have a computational thinking pathway. And you can see that computational thinking is the problem-solving process that helps in the computer science world, but in every aspect of living. And CT includes formulating problems, thinking logically, abstractly, thinking analytically, and it also includes dispositions. And so some of the dispositions and attitudes include confidence dealing with ambiguity, tolerance for ambiguity, persistence in working through difficult problems, and the ability to communicate well with others. And so when we look at that overview, that definition of what computational thinking is, We also use a really more carefully laid out vocabulary, and that vocabulary you can see is found in ISTE. And some of the things we do is we design our lessons so that they include data collection, data analysis, problem decomposition, algorithmic thinking, and procedures. So you can later investigate this more deeply, but this chart is really helpful when you're laying out your lesson plans and your pathway for your students. So in our district, at each grade level, computational thinking is vertically aligned, and it grows progressively deeper and more complex through a series of graduated and interrelated projects. And so you can see that at every grade level, they're working with sensors and motors and programming in block-based code up until 8th grade. They're programming all different sensors and motors, Arduino boards, and they're problem solving through coding and design. And then as they get into the older areas, we move into 8th grade Python. All students, all students K through 8 have had block-based code in many different ways and forms. But then when they reach 8th grade, they're required to have an 8th grade Python course. And so you can see how we're building that. And then as through high school, it's no longer mandatory in high school. We have to create opportunities for them. So we have a pathway that is Python 1, Python 2, coming up Python 3. We have APCSA, APCSP. We've started a cybersecurity course and a data analysis course. But on top of that, we're embedding computational thinking into all areas, and that will take some time, and that is our goal. So what you'll see here is just the way we used to describe our pathway. We used to describe it in terms of the equipment we used, but then we realized that you can use equipment in 2nd grade that you can use in high school. It's the way you use it, it's the problem-solving sets that you work with. And so on this picture, this is just an example, everything above the line is in the curriculum. Everything below the line are interconnected after-school programs that were designed to connect to that curriculum area. So you create an ecosystem that students can move in and out and in between. And so you can see how it developed through time. So what we've done now is, instead of interpreting computational thinking in terms of tools, we've now redesigned our lesson plans so that they include computational thinking practices and competencies and student artifacts. And then on top of that, our overriding concept is student agency. So the idea is, if you're going to create a lesson plan, where have you allowed for creativity and personalized learning to take place? So before you even write that lesson, and before you even address those competencies, you're making sure that there's room for creativity in those lessons. So you can see what they look like. At a certain point at the lesson, we have a assessment where it's almost like an exit interview. Were the students able to write the code? Were they able to get their voting machine to work? Are they able to correctly identify some of the tools and concepts that they learned? So that is a quick example. The reason I provide you that is because we are working right now on a PA Smart Advancing Grant, and we are working with 7 school districts. Is anyone here from Carmichael, Jefferson Morgan, Brownsville, Beechwood, Manchester, Pittsburgh, and our team? We are working with rural and urban schools because they're a microcosm of the school districts in the state. And these are underserved, under-resourced districts, and we provide our lesson plans to them, training at the Summer Institute. Of course, anyone can attend the Summer Institute from across the state. The Institute is June 15th through 18th this year, and basically we teach all our curriculum and help you jumpstart your vertical alignment. So on top of that, we have another grant, and it's an NSF grant for 3 years. It's $1 million grant, and it's the idea of building these pathways for this reason, it's an economic redevelopment program. The area has lost its coal industry, And for generations, that's all the families knew. So now we're helping to change their thinking to help address the new future of work for these families by helping their children develop these pathways so they'll have a future in a new area, a phase of work. And so what will happen as you connect with us is we'll soon post a website, and that website will actually show the lessons, give you the lesson plans. It'll have all that information for you that you can just take and use as you like. And then later we ask if you would help us by co-creating your own lessons and helping us get them out to other people. So the idea that your population might be different than ours and culturally different in many ways, and we want to address all needs for all children. So that's what we'll do together. So within this pathway, there are 4 distinct through lines, and we're really going to deal with the spatial reasoning and discrete math today, and you can see how computer science really addresses those needs. The 4 through lines are maker education, artistic expression and creativity. You can see that in our lessons. Computational thinking, which is a problem-solving process, and you can see it through the coding, the virtual and physical space. Manufacturing and design, that's engineering, human-centered design thinking. All of these are addressed in that pathway. And an example of manufacturing is kids at a very young age will use blocks CAD in 3rd, 4th, and 5th grade. By the time they reach middle school, they go right into CAD, and then from high school they graduate into a higher CAD system. So you can see how that manufacturing and design and human-centered thinking takes place. So really, spatial reasoning and discrete math is really what we're going to focus on now, and the ability to visualize in 3 dimensions.
So she was just, Ms. Owens was just talking about the different through lines, and you'll see throughout some of the lessons and the activities I'm going to show you today that those things are going to come through, but our concentration today is really going to be on math. And so I'm going to pick out 3 of the areas that I teach in technology literacy class that are also reinforced in our STEAM classes. The first one is Scratch. The second one is blocks CAD, and then the third one is Spheros, using the little robots to program. So I'm going to start with Scratch because that's what we use as our foundation for computer programming. We start at the elementary school with Scratch Junior, and then by the time the students get to the intermediate school in 3rd grade, students will all have a Scratch account. And so the very first lesson, immediately math is already introduced. Because in the very first lesson, we have I have to introduce the XY coordinate grid, because when you tell the kids, we're going to bring a scratch count out onto the screen and have him move 10 steps, and they press the button and it goes just a little bit, and they're like, but wait, I wanted it to move 10 steps. Well, 10 steps is actually 10 points on the XY coordinate grid. So if you teach any of these things about XY coordinate grid, those are the things that are then being reinforced in the Scratch, through some of my Scratch lessons. And you'll see this come up again and again and again in some of the examples that I give. This morning, whenever we were listening to the keynote speaker, he said that one of the greatest ways to learn and study is through recall. And so a lot of these things are already happening in the regular classroom where they are learning these XY grids, but now they're reinforcing it and they're recalling that knowledge from their math classes. It's amazing whenever I ask, okay, students, how many of you have seen an XY coordinate grid? And a lot of them at first are like, maybe. And then I say, okay, well, what about like anybody play Battleship? Immediately, hands all go up, and then you build that connection from what happens in the real world to what's happening on the screen. So in the very first lessons that I give with Scratch, we're already looking at math. I just grabbed a bunch of blocks from the Scratch codes, and I just brought them out and I said, look at all the ones that just rely upon math. And these aren't all of them. These are just the most common ones that I use on a regular basis. Whether it's pointing in the correct direction whenever you're having your character go to the right or to the left, moving, if you're thinking about spatial reasoning, even going forward and backwards, one layer, when you have something going in front of something or something behind in a 2-dimensional world, that's the only way you can do it, is by having those layers. Changing X by, setting X by, changing all of their locations on that XY grid. Even whenever you have relationships between changing size by 10 as opposed to setting size to 100%. and then there's all the operators, the addition, subtraction, multiplication, divisions, picking random numbers. We use that a lot, especially when we start to get into our video game unit. Kids love using that. Setting variables and collecting and storing data, that all happens under whenever you are you're making a variable, whether that variable is score or points or lives or whatever. They are all data collection. It's a way of storing data on the computer. And then again, having relationships like using the microphone to set the loudness. So here's an example of an art project that a student created using we were actually defining a block, and so we had draw a shape. And so this incorporates a little bit of geometry, so you can actually see as you go through this, setting the position in the very center, pointing in the right direction, repeating so many times, changing direction, and then drawing this shape. And the shape is nothing more than repeating a number of sides, moving so many steps, that's the actual size of the object, and then turning so many degrees. That's 360 divided by the number of sides, and that gives you the internal angle. And they do this for the first time in Scratch, but you're going to see this same or similar formula come up later on in Spheros. So here's an example of this project. I already have it open here, so I'll just put it there. And of course, self-expression, adding music to it to make it more fun, more interesting, finding it fun. And you don't even realize what it's making as you're watching it, or you might have a hint as you listen to Okay, so this is taking longer than I remember it taking, but it does make a nice sound. Now, of course, we're going to stick on the bottom, and I think at one point, didn't quite match. There it was, the bite of the so, okay, whoops, no, let's not do that again. So that's showing math in an art project within Scratch. Another example is using math in video games, as I was talking about earlier, using that randomizer button. This one, I'll just go to the phone game here. And you'll notice right away that I do have my students use the commenting codes over and over again. I had a computer science professor. I asked him, what is one thing that you want me to really reinforce with students at a very young age? And he says, get them to comment on their codes, because that's something that all computer programmers do. So I do have the students start to comment. Even if they're copying some of my codes from me, I tell them, you can copy, but you got to tell me what it does. So then that just reinforces their skills. So in this case, we have a general palm game. If you're looking at the code for the ball that is going to fall, I have the students decide that we're going to put the ball at the top of the page. That's what this here does. We set the ball to a little bit of a smaller size. And then it says point and direction, pick random 100 to 260. So it's picking a random direction to go downward. So if you think of the 360, you're actually adding 10 onto 90, that way it's not going back and forth. Add 10 to 90 and you get 100, subtract 10 from 270, and then you have it going downward somewhere between here and here. And so I draw that up on the board. The students can then have a better understanding so that whenever you actually play the game, the ball starts at the top. Oh, I missed it. And then it's programmed to also bounce upward. So if it's touching paddle, the direction that it's pointing is just the opposite direction here. So we're pointing negative 90 or negative 80 to 80. So any questions so far? Good. All right. So that is math in video games. Then whenever we introduce BlocksCAD, the very first activity, or one of the first activities we do with BlocksCAD, is introduce them to the z-axis. So they've been used to that XY plane. Now we're adding that third dimension. So we're saying we're taking that XY plane, we're laying it down, and we're adding a z. to it. And whenever you do that, the students sometimes have a hard time grasping that, so we want them to live that in the real world. So we actually take one of our back STEAM studios and we turn it into an X, Y, Z coordinate grid. And we give the kids yardsticks and computers, and they go to, and then we have things hanging from the room or sitting on the floor, and they actually have to go and measure the location on an X, Y, Z coordinate grid. I don't know if you can see this well enough, but we have X and Y on the bottom. Z is this tape that's going up to the ceiling. And so there are things that are hanging from the ceiling. I think we label even the projector as an object that they have to get. There is a globe that's hanging back here all the way from the ceiling. So they're measuring in 3 different places. They're measuring the X, the Y, and the Z going up as well. And what they do with this is they put that onto a chart, and they're working in teams. So half of their team is in the back doing the measuring, the other half of the team is in the front of the classroom, and they're taking those coordinates and the information on a shared Google Doc, and they are recreating that in BlocksCAD. And so the picture that you saw on that previous slide, this is actually a recreation of the space in the back of the room. It's one of the it's a great unit because students are using measuring. They're using communicating back and forth as a team member, and then they're also getting used to that X, Y, Z coordinate plane and really starting to understand that spatial reasoning. So in BlocksCAD, most of the blocks deal with math. Most of them do. But to start, we just concentrate on the shapes, and then just a couple things like translating and rotating. And this is what we do in 3rd, 4th, and 5th grade. So after they go through the process of living in that virtual space, the X, Y, Z coordinate grid, or the physical space, then we take it to a virtual, and the very first thing that we have them create is a snowman. Now I'm not going to show you the video because it takes really a long time, but instead I'm actually going to show you how to build a snowman using BlocksCAD. So if you've never done this and you're not familiar with BlocksCAD, we start off, if you look at it, it's very similar looking to Scratch. So the students are already used to that block-based code. They see over on the left side all of the blocks, and then on the right side, this is the rendering area. This is where things happen. The only difference is that you're not going to have things physically move and tell a story and play games and things like that. You're actually building 3D models of things. And I also tell the students, because right away they see the 3D printers in the back of the room, and they're like, oh, are we going to print something? And I'm going to tell them 90% of the things that they create are not going to be printed. In fact, maybe 1 thing or 2 things that they actually create are going to actually be printed. Everything else happens in the virtual world, but they're still learning that the BlocksCAD. We teach over 800 students in the intermediate school, so for us to actually print everything, you could see that would take days. So actually months. So we don't print everything, but the lessons that come with BlocksCAD, many of them you can print, and some of them you have to do a little bit of modification to make them being able to print. So we are. I'm going to just walk through building a snowman, in case you're not familiar with or you've never used this. So right off the bat, we talk about geometry. What shapes make up a snowman, if you're looking at these? Of course, a sphere. Yes, spheres. Multiple spheres. We start with, we're going to start at the bottom and just work our way up, because you don't want the thing hanging up here and falling down, right? So we're going to start with the sphere on the bottom. I'm not going to change anything here. This is where you can also start talking about the geometric formulas, like r equals 2d, so that the students understand radius is twice the diameter. And that's going to become very important whenever they start to position things in this world. So the very first thing we're going to put out is a sphere. And you'll notice whenever I render it, it ends up halfway above and halfway below the XY plane. And so because of that, if you were going to actually print this, everything below that plane would not print whenever you go to translate it over and create the STL file. It doesn't actually print. So what we need to do is actually move it upward. So we're going to, this is the first time we have the students translate something. We're going to move it on that XYZ coordinate grid, and Z is going upward. So if the radius is 10, in order to get it just to sit right on the XY plane, then we need to change the Z by 10, a positive 10. And again, if we render that, you'll see now it is sitting completely above the XY plane. So the next object that we are going to put on the snowman is the center sphere. So again, we're going to bring out another sphere, but this one is a little bit smaller. And we're going to put it, make it with a radius of 8. And again, if you render it right away, it puts it underneath the bottom sphere, actually right in the middle of the bottom of it. So we need to now translate this one up on top of it. So this is where we do a little bit of math. I draw it out on the board a little bit just to give them a greater understanding. We know that the center of the bottom snowball or sphere is actually on is at 10. So that means the top of it would be at r equals 2d, yeah, 20. So it's at 20. And so if you're going to bring this other sphere up on top of it, so it just sits on here, then we need to bring it up to 28. Translate this up. And again, students are used to using the block base code, how they snap together, things like that. So we go to 28, but then I always hold up two rolls of tape, and I put them on top of each other. I'm like, is it going to stay there? And of course, the one falls off the other one, and I tell them you're going to have to squish it down. So we used math, exact math to start, but then you may need to do a little bit of experimenting and iterating. So that's another computational thinking concept that we put into the lesson. And so in this case, at 28, we're going to bring it down maybe to, say, 26, and see how that looks. Maybe 25. And this is where they're doing a little bit of guess and check, and then finally it looks like it's sitting right there. So you repeat this process again, and I'm just going to show them how to duplicate this, and we're going to do it for our final top one, which will make it 6. The center of this one, if it was at 25, we're going to add 8 to it and get 33, which means we add 6 more to it in order to get the center point, so it's just sitting on top. So 33 plus 6. Oops, way too high. So 3. There we go. And then if you need to, you can also squish that one down a little bit. We're going to take it down to 37. Alright, so now we have our snowman. Now the fun part is then giving him arms. So arms are going to be what shape? A cylinder, yeah. And actually, before I do that, I'm going to take these 3 things, and I'm going to go to my setups, and I'm going to join them together, because these are the parts that make up the body. And I can actually give myself a comment on here. I'll just call this body. Okay, and hide that. So once I have the body, then I can go ahead and put the cylinder on it. This cylinder is going to be a tall cylinder. And if you think about it, if the center, if the diameter of the center is 16, because the radius is 8, then if you double that, you get 32. So let's make the height of this 32. And you'll notice whenever I render this, you can't, let's make it a lot smaller. Let's make it down to 2. Render it, and you won't be able to see it because it's actually in the middle of the snowman. So I'm going to right click on the body, and I'm going to disable these blocks. And when you disable the blocks, then you now have you can now see just the arm itself. I'm actually going to make this a little bit smaller. And you notice with the cylinder, whenever you create it, you have a radius that is locked here. If you unlock that, then you can make a cone. So if you're going to make his nose later on, you can unlock that, and the bottom radius can be 1, and the second radius can be 0. So you can make that cone shape. If you leave it locked, then it makes the radius at the bottom and the top the same, which is a perfect cylinder. So remember that, make it smaller. But the problem is it's going straight up and down. So now we need to, this is where we're talking about our spatial reasoning, where we need to rotate it, and go to here. And I love doing this with the students. because rotation is one of the hardest things for them to understand. So I have them all hold their hands like this. So make an L and then stick your middle finger straight up this way. And whenever you do that, you have an X, a Y, and a Z axis. So if you're going to rotate around X, if you hold this still, and that's the way it's going to rotate. Y is this way, and then Z would be just rotating around like that. So for the students to understand that, then we can look at that XY plane, and we can say, well, we don't want to have it rotate around the Y, because then it would just spin. So we want it to actually fall and lay down maybe this way here. So we'll rotate it across the Y axis, which is this one here. So if we do that, we can change this to 90 degrees, have that fall, and you can see it's there. But if we were to put it there, then it's sticking out a little bit. So one of the properties of the cylinder is that you can center it. So I'm going to actually center it. And then the next thing I need to do is raise it up so it's in the center of the body. And the body was at 25, so we'll go a little bit higher than 25, and let's go ahead and raise it up. So I have to wrap a translate around all of this. I'll raise this up, 27, and I now have. So we now have the snowman with the arms going straight through. You can add more to it. The students then also add a hat onto it, which is just 2 cylinders. One is a very thin cylinder. The other one is a taller cylinder. It looks like a nice hat. And then the cone, they practice the same process of making that, taking the cylinder, turning it into a cone, rotating it, and then translating it. This is also where I talk about the order of operations, because if I take and I split these and I translate it first and then rotate it, I get a completely different result. So in this case, whenever I translated first, it moved it up, but then the whole thing rotated down, and it ended up on the floor. And so doing these in the correct order is very important. So they need to rotate it first and then translate it in order to get it into the correct position. So my video went a lot longer because I also had a hat on it and a nose, but I think you guys get the idea, right? You can color these too. Under setups, you have, or excuse me, transform. You can color these, and this is where kids really love to come in and just make an actual white snowman with a stick that for arms is it's brown. There we go. And then the hat would be black, the nose would be orange. Good. So that is BlocksCAD actually creating a snowman. The BlocksCAD website itself, and everybody who is in attendance here today, you will actually receive a free BlocksCAD account through the end of this year. So if you'd like to do that, we have Jay's in the back here. He can hook you up with that. And if you'd like a free account, you can go and check in with him. With a free account, it's pretty cool. I'll go ahead and show you a couple of the neat things that we use. It is integrated with Google Classroom, so you can assign lessons and activities to your students through Google Classroom. And so if, this is just a screenshot of the opening page. This one, yeah, okay. So you can search by what grade level you teach. You can also search by what concept or skill that you are trying to teach. So if you want to teach volume, there's activities that relate to volume. If you're doing fractions, angles, there are all sorts of activities. We start in 3rd grade with the students building a snowman, then they build a caterpillar, and then we try out other things. In STEAM class then, we actually had the students create little cookie cutters, and we had reading groups who would go to the elementary school, and they would, so we had 5th graders who would create cookie cutters that would go along with a children's book. And then they would take it to the elementary school, they would read the book with the kindergarten student, and then they would give them a little cookie cutter that they could play with Play-Doh. And so as they're reading, the kids can be playing around with it while they're hearing the story. So it's a really neat activity that we work out with our elementary and our intermediate school combined. So BlocksCAD is, like I said, it's a great tool. There are other teacher resources on this website as well. I don't know if it might not be, oh, So there's manuals, there's activities, there are videos to help you out. There's blocks, and then you can see how they are aligned to the standards. So Jay's going to be passing around a sheet. You can go ahead and put your contact information on there, and if you want a free subscription for the end of the year, then you can put that on there. Do I have any questions about BlockScan before I move on? Okay, no questions. All right, so the next unit that we also do, that I teach is Spheros. Has anybody ever used Spheros before? Spheros are a lot of fun. The kids really love doing this, and there's a lot of applications with math. And the more important thing, or the thing that we really find powerful with the Spheros, is the data analyzation, so that you get instant feedback from the Sphero whenever it travels or when you program it to do something. So this is just an example lesson that I do with my students. This is one of the very first things. It is it's based off of Blocks 1. So if you are familiar with the Sphero EDU site, I took the Blocks 1 course and then I modified it a little bit. I added a little bit of the scientific method to it so that the students are experimenting and iterating. They're also looking at data, and then they're making decisions based upon the data. So this is just a basic lesson that I would have. So this is a basic lesson that I would have for the kids. We start off by partnering up and doing an unplugged activity. So instead of jumping right in to Spheros, I actually have them program each other to walk in a square, and they have to be very purposeful about the language that they use, so that they are making that perfect square. So the students then, after they do that, they can decide, okay, what might this look like in BlockScan, or excuse me, in Sphero itself. So, so they'll take some ideas from their pseudocode. They'll create a program to make their Sphero travel in a square, and in the program, there's just directions here. So the very first thing that they try out is this rolling in 4 different directions. So they roll at 0, they roll at 90, they roll at 180, they roll at 270. The speed and the time that it rolls is all going to be the same. That'll give them the same length on the sides. So there's questions that they'll actually look at, they'll analyze and the code, they'll predict what it might look like, and then they run the program. After they run it, they'll realize that it actually makes more of a circle because they didn't stop it before it returned back to its original position, because every time it gets to a corner, it just turns, and so the corners are actually rounded. So the students learn that, okay, we have to make the Sphero stop, turn, go, stop, turn. So we put a delay in between each one. And then they look at this, and I'm like, okay, so when we see this code, what do you notice about it right away? And they see that there's a lot of repeats to it. They're doing the same thing over and over again. They're only changing one variable along the way. And so I'm like, okay, well, how can we use math and the sensors in order to make that square and refactor our code to make it more simple? And I always tell them that, like, I used to be a musician. I say, like musicians, computer programmers are lazy. We like to make things as efficient as possible, and so this is one way we do that. We shorten our code to make it a lot more efficient on as we program it. So I show them how to refactor the code where they take the heading sensor and then add 90 degrees to it, and everything else pretty much stays the same. And that's what they put in here. So we start off with a heading of 0. Right away we turn 90 degrees and then move forward, and then delay, turn 90 degrees, move forward, and they loop this, doing these 2 things 4 times. And then I ask them, all right, what does the 4 represent? What does the 90 represent? And then they run the program, and they'll see that it actually makes a square. Now, sometimes whenever they make the square, it doesn't make a perfect square. And I'll show you some pictures in a couple minutes. And then I say, okay, if it's not making a perfect square, what are some things that you need to do to change? And so they have all of these different questions they're going to answer. Change one of the variables. So here we're talking about the scientific method. Change one of the variables, predict what will happen when you run the code, and then tell me, how did your square change? And they're looking at that and analyzing the data again. And so they'll go through each one of these. And so their graph, the very first one, the Sphero might kind of look like this. Now, I am going to have full disclosure here. I actually stole this from my daughter because she used this as her science fair project this year, how to make a perfect square. And instead of using the actual Sphero bolt, she used the BB-8 Sphero. And with the BB-8, it's kind of top heavy sometimes, and so it rocks when it moves, and the head moves like this. And so whenever she moved at a very slow speed, you can see it actually rocked a lot. And so by going at a speed of 60, it rocked too much, and this one actually might be for the 1 second one, but then after changing some of the variables, she found that she was able to make a more perfect square because if you have it rolling at a higher speed and for a longer period of time, it's able to correct itself quicker before as it's going into shape. So she was able to then make that perfect square. From here, when we talk about geometry, students can create a regular polygon. The formula is the exact same, and thinking back to that lollipop activity earlier, all they're doing is changing two variables. The first one is how many times it repeats. That's going to tell you how many sides. So if we have an octagon, you're going to put an 8 in here. You have a pentagon, you put a 5 in here. And then the heading, the angle is also going to change. And sometimes the kids forget to change this one, and so they will run a pentagon and leave it at 90 degrees, and all they have is a square with one extra side. Because it just turned one more time. And so they have to understand that you need to come up with another number here. And so in order to do that, they remember back to the activity we did with the lollipop. They were able to then divide 360 by the number of sides, and that gives you that internal angle for where it's going to turn. And so in this case, the heading, it would be, if we had a pentagon, it would be heading plus 72 in order to give us that perfect pentagon. And then once again, they just run through that exact same, describes it just what I told you. They run through the program one more time, again changing those variables, seeing if it's the same. They made a perfect square. Do those same variables work for your perfect polygon, whatever other polygon you created? And of course, the students, they always love, they quickly realize that, because they always want to, anytime they put in a variable, they always want to push the limits, right? So they say at 60 speed for 99999999999 seconds. And I'm like, why did you do that? And you can really tell. The kids who don't understand programming and are just experimenting, they're the ones who are going to be going 9999999 and not really thinking through, because I tell them, okay, we can let this go and it's going to run until the battery dies or it hits a wall. It's going to hit a wall first, because otherwise it's going to run for 7.5 weeks. So they really need to understand what these numbers mean, because if they make let's say an octagon and have it run for 2 seconds, that octagon is now bigger than the pentagon running for 2 seconds, and so it may actually hit the wall a lot quicker. And then after we do that, we also change the physical properties of the Sphero. We will either run it on carpet instead of on tile, or maybe there's a rubber sleeve that you can wrap around it, and we'll have it run on there. And again, we're seeing if their polygon is improving. Again, it's a scientific method. This is a new variable that they're changing. In this case, it's a physical variable instead of a programming one. So the last thing I wanted to show you with the Spheros is these graphs. These are actually 2 videos that come from the Sphero EDU lessons. The first one it kind of describes the accelerometer and how it is graphed. So I'm going to go ahead and show you this video here.
Now you will write the main logic of the game. You can try this on your own without the video, or follow along here for a step-by-step guide.
So what they're actually programming is a toss game, where every time you toss the Sphero, it detects whether or not it's being thrown, and you'll see that in just a second. So they have to write a conditional that says if it's being thrown and the accelerometer is greater than 3, then you play an animal sound. And so that means that every time it's thrown, it plays an animal sound, and then the person who catches it actually has to tell you what animal sound it played. The sound comes from the computer, but the game is still kind of the same. You frequency.
In Blocks 1, you learned how to program a square with a loop. This time, you will use a new kind of loop called Loop Forever. Remember, a loop enables you to nest other blocks within it and repeat those blocks as many times as you want. For the toss game, you want the program to loop until you're done playing, so it continually evaluates the toss condition. Go to Controls and add a Loop Forever block below the speed block. Loop Forever means the program will repeat the logic within it forever, or until you stop the program. Now you need to add an if-then-else condition inside the Loop Forever block. This block allows you to evaluate if a condition is true before calling the logic within, or else it will execute an alternate set of logic. For the toss game, you want the program to recognize each time you toss Sphero.
Okay,
To
so
do
that's
this,
generally,
you
I'm
will
going
need
to go
to use
to
a category and
the
drag
actual chart so you can see what
three.
that looks like. There it is. So this is what it looks like whenever you actually throw the Sphero.
G's means. Toggle
This is
off
live
the
feedback
X,
that
Y,
you're
and
receiving
Z
from it.
axis.
On the iPad,
You
it
only
comes back
need to
as
look
live
at the
feedback,
total
but on
acceleration
a
of this.
PC or computer, the app,
Knowing
you
that
actually have to
1G
show
is
it after you
resting,
run the program.
shake Sphero just slightly, noticing it reads just over 1G. Now toss Sphero about 2 feet in the air and catch it. You'll see an accelerometer spike well over 3 Gs. So now you see how the toss game works. You throw the robot, the sensor reads the intensity of the throw, and then you can write some conditional logic to follow the toss inside of your if-then-else statement.
So
Continue
that's-
to the next step to fill in the code for the conditional logic.
That's the accelerometer. The other one is the gyroscope. And on this one, it
Run
will
the
actually
program again,
detect
but this
whether
time,
it's rolling,
hold the live sensor data tab
or
at the
spinning,
bottom
or
and
tilting.
scroll over to the gyroscope values. Now toggle off the pitch and roll axis that you are not using in this program. Now when you spin Sphero counterclockwise and it turns green, notice the yaw spin rate value spikes, and you get it all the way up to 2,000 degrees per second if you spin it really fast. Now spin it clockwise and it turns red. Notice the yaw spin rate value drops below 0, all the way down to negative 2,000 degrees per second.
So there's a lot of other activities that I haven't had a chance to get into yet because this is our first year with Spheros. There was one that was I just saw last week that was analyze the graph, and so you would look at a graph of a path that it would follow, and then you actually had to write a program so that the Sphero would do the same thing. Hopefully through these 3 different programs, the Scratch, through BlockSCAD, through Spheros, you can see how students at South Fayette use that math through line with spatial reasoning and analyzing data in order to learn computational thinking. Does anybody have any questions?
The reason we really showed you these 2 concepts, spatial reasoning and discrete math, is because discrete math is the mathematics that computer science is built from. And students have to have a solid understanding of graph theory and mathematical modeling. So as you can see the work Shad does with his students, we use Sphero a lot for the mathematical modeling, for understanding that. The spatial reasoning is really important because there's research that shows that if kids can understand in their mind what 3D shapes look like and that sense of dimension, that they do better in all math subjects. And another better example is many of us, when we were growing up, we understood that organic chemistry was a weed-out class for med school. And the reason it's so hard for students is because it's the first math or first chemistry that was ever visual. You have to understand how components and molecules move and form. And so to understand that, this is, again, the beginnings of having that reference, that understanding of spatial reasoning. So really that's why we took you along this pathway today, and we hope that it was helpful for you. In the future, very soon, we'll have posted our lessons from the PA Smart Grant that, again, you can take whatever you want no charge. It's just for sharing and for helping all of us raise the level of computer science for all students. So we thank you for being here. No questions? All right. Can have an early lunch. And in the back, if you needed, if you would like to talk to anyone from BlocksCAD, they're happy to provide you with that free option for this week. Thank you.
I'll send everybody a follow-up email from BlocksCAD if you're interested in continuing consuming the round. We don't have a booth.